All right, let's get started. So we are going to introduce the concept of alternating current machines. And in the past, they used to start out with DC machines, but now we're doing AC machines. Anybody want to guess why we do AC instead of DC? Yeah, you come across a lot of DC machines in your life, do you? Not many, right? Even those really cheap ones that you find in toys and stuff like that, they're pretty simple with AC machines. With DC machines, there's a little more complexity. So you might find some DC machines more like for cordless power equipment or even corded power equipment because you're trying to maintain a lot of speed control. And AC machines don't do that very well. That's the problem with That's the issue, if you will, with AC machines. If you have to do speed control, you really have to do a lot of work. Where a DC machine, it's a little easier, or quite a bit easier actually, to do speed control. In fact, there is an alternating value inside the DC machine. It just doesn't appear from that perspective. So all the stuff that we do with magnetics, and we've already talked about this, it has to be alternating current. Anytime you have a coil of winding around a magnet, if you hit it with DC, it's just going to look like an inductor and short out over time. So with AC, it's better to start off with AC because that's most likely what you're going to end up using in industry, regardless of the industry you use. If you work in an industrial environment, like if you work at a paper mill, if you work at a fab facility that is making widgets, you're more inclined to find AC machines, unless it's like a servo applicator where you're doing it with a specific position. We're trying to maintain position. And most DC machines tend to be very small in size. Some of the biggest DC machines you'll find tend to be for like conveyor systems. So if you're moving a lot of product up and down a conveyor, using a DC machine works really well because you can apply a braking force on it and maintain its position. Where again, AC machines, you can break an AC machine, like physically slow it down, but to maintain in that holding position is much, much tougher for an AC machine. So there are some advantages to DC machines, but if we have time, we'll get into some of the DC concepts, but we'll focus on here. The other nice thing about an AC machine is most AC machines can operate as a motor or a generator. It can do either one. So that's why we introduce them as AC machines and not say AC motors or AC generators. When we get more specialized into the topics, we'll actually discuss that. But the concept is like any machine, AC machine can operate as a motor and generator. So like electric vehicles or hybrid vehicles, one of the advantages of using a hybrid vehicle is because the brake system, right, the regenerative braking, term most of you probably have heard, that's where a hybrid really gets the big bang for its buck, is because of that regenerative braking. When you apply your brake, unless you stomp on it, you hardly use your brake pads at all. You're relying on that regenerative braking to take energy out of the wheels and reduce the momentum of the car, and you're pulling that energy out and then you're sending it back to a battery pack. Okay, that's the regenerating brake component. But I don't think that would be necessarily a good design if I had to have a machine that was a motor, let's say, for the brake, and then I would need a separate machine to operate as a generator, right? Because not a generator, because at one point, no, the braking is the generator, the motor would be the driving it. So you need a bunch of different shafts. So it would make things a lot more complicated. So what you end up having is you just have one piece of equipment that does the braking as well as the prime moving or moving it forward. So an application like any hybrid vehicle has the ability to do that. And how many of you all here have a hybrid vehicle, a hybrid powertrain? None? Really? Somebody rocking a Prius, trying to look cool? They are?
Yeah.
Well, I supposedly that's becoming like there's a Toyota minivan that comes out that only is available in a hybrid version. And I thought Hyundai had one of their cars or a few of their cars that came with hybrid powertrains that was supposed to be about the same cost. But you're all young, so you're probably into performance. So hybrid vehicles aren't necessarily performance-packed vehicles. Although, anybody here into hypercars? Anybody know what a hypercar is? What is a hypercar?
Kind of like some good stuff. This is more like, can it do more hybrid stuff as well?
So the name is in the title, but if you look at the hypercars, the first generation, there was a P1, McLaren P1. I think it was the Porsche 918, and then it was the LaFerrari. And why'd they call them hypercars? Aren't they supercars? Aren't they super duper cars? No, they call them hypercars because they were hybrid power technology. So those vehicles, and they were the pinnacle. This is, I don't know, 10 years ago. They were the pinnacle of performance because they used hybrid technology so they could get a lot of power, 1,000 horsepower, without needing a massively sized engine. And if you look at, anybody know Formula One? There's a Formula One E coming up, if it's not already available. Maybe it's already there. I haven't seen any races, but you actually can have electric vehicles do Formula One racing. And they've actually banned hybrid vehicle technology from Formula One because it would just be not a fair competition. So right now, because of EVs and stuff, you saw at one point, Tesla's doing quite well, but all the other car manufacturers seem to be struggling with producing electric vehicles. And that has a lot to do with price. Cost is a big part of it. But I think more and more as we're trying to get more efficient vehicles, because you want to pay, you want to get 40 miles to the gallon as opposed to 20, the hybrid power technology or hybrid powertrain technology is here to stay. And those are all done by AC motors. Like the Tesla machine, we talked about this class already, it was originally a Tesla motor. Now it's just a synchronous machine, an AC synchronous machine. So maybe I should use that to say many used in industrial facilities and in EVs for power itself. So just a couple of things we have to understand a little bit about hybrid power technology or AC machines, I should say, is you have to get the concept of motion based on having a magnetic field and a current carrying wire. You're going to get motion in the perpendicular plane to that you join by your fingers. So your magnetic field points in one direction, your middle finger points in the direction of current, and then your thumb, if you are flexible enough, I'm not flexible enough, will point in the direction of where force is applied, okay? That would be the concept of generator action, and you use Fleming's right-hand rule. And what you're trying to do is if you have motion here, you're going to drive a current in this direction. So the concept is you're driving current because you're converting mechanical energy to electrical energy in a generator. So this current here has to be supplied by that generator. So you have an equivalent EMF to drive that current. You need to generate enough of a voltage to drive the current so that you have that induced torque. So without getting into a lot of detail, and this is the text. If you look at one of the recommended textbooks, this is one of the figures that are in the textbook, but it basically shows you how you get an induced voltage from a rotating magnetic field or a coil. But we can simplify it down, and our induced voltage on a wire that's rotated in a magnetic field is going to look like a pretty good sine wave. As long as that that generator is built reasonably well enough, you actually get a pretty nice sine wave, which is what we want. We want nice, clean AC coming out of our generators. Otherwise, we have lots and lots of problems. So if you don't have a sinusoidal waveform, how do you characterize its relationship or its physical manifestation, or how do you analyze a system and how do you figure out what to do with it? Should be a mathematical tool. I know all the ECE students who've had 314 know what it is. And EETs, if you had 324 with me, you would know what it is.
That for you.
Fourier series, right? Fourier series or Fourier transforms. Anybody here taking 314? Do they still cover Fourier series? Yeah. So the way that you represent a periodic waveform, okay, no matter how ugly it is, you just take the fundamental, any DC offset, and you just start adding harmonics to it. Harmonics usually are bad because they don't necessarily do what you want it to do. So as much as you can, you try to just have your fundamental frequency. It's the same thing in motors, but motors generally are so good at putting out clean 60 hertz that there's never been a parameter called THD that I'm aware of for production inside of a synchronous machine or an induction machine. So now we're going to do our next step, which is motor action. So we're going to use our left-hand rule. So thrust, field, current. Again, we're just getting a slightly different one, so we have to use our left hand. and you can see the motion because now we're moving our motor. So we got to get mechanical torque doing it. And that force is always going to be perpendicular to the current flow. So the motor stays inside the shaft. So you're basically getting perpendicular forces on the perimeter of the shaft. And it's always rotational torque. You can make a linear action. Yes, sir. Am I off by a day?
Yeah.
Let me look at the syllabus. I might have put them in the wrong spot. Let's see. Oh, let's see. That was chapter. Oh, you're right. Sorry. I forgot about end of chapter 2. So we'll pick this up on Thursday. Actually, no, we won't even pick it up on Thursday. Because Thursday will be the exam 1 review, right? So maybe we'll just start over again. Okay. Oh, let's finish transformers. Sorry about that. I'm a day off. I could have sworn, and I have all my notes here. They're usually much more prepared, but I should have looked at the syllabus. Next time I will look at my syllabus. So finish up transformers. Okay. Oh, it's too quick. Uh-oh, not waking up. Well. Okay, one thing about a transformer is how much the voltage drops across that transformer. So we'll define this as voltage regulation, which hopefully we've seen voltage regulation a bunch of times already. If you haven't, it's no big deal. You're basically just looking at the quality of a power supply. So how much the voltage drop isn't really a good indicator, because if I told you something drops 5 volts, that could be good or could be bad. A 5-volt drop off of a 5-volt power supply is pretty bad, but a 5-volt drop off of a 1,000-volt power supply isn't that big of a deal. So what's more appropriate is what is the percent change or the voltage regulation, which is V no load minus V full load. So how much that voltage is above its full load value, what the delta is, divided by what the voltage should be under full load conditions. So the higher the drop, the worse the voltage regulation of a transformer tends to be. So here's a simple example. Here's a single phase transformer. It's rated 100 kVA, 200 to 400 volts. And its internal impedance, the X equivalent, we're only going to focus on X equivalent because we're going to assume that our equivalent is so small in our equivalent transformer model that we can neglect any voltage drop. So we're going to assume that its X equivalent, and we can call it also short circuit reactance, is 0.1 ohm. We want to compute the voltage regulation when the transformer is fully loaded at unity power factor and rated voltage. So the first thing we need to do, move this up, is we need to calculate what that current is going to be to deliver full load to, in this case, the 400-volt supply or the 400-volt side of the transformer. And it's going to be at unity power factor. So at unity power factor, that tells me that angle is going to be 0. Okay. So I equals S over V conjugate, pretty easy because both the angles are 0. So there is no value. And we have 250 amps at an angle of 0, which hopefully is what makes sense to you because at unity power factor, the voltage and the current are going to be in phase with each other. So now to solve for the voltage here, this is the transformer. So the transformer on the high side is basically here. I got a voltage drop over here. So what I'm going to do is include the voltage drop, and I see that my voltage goes to 400.8. Now, what that means is I have to adjust this voltage over here to operate at 400.8 volts because I want 400 volts over here. Anybody remember why we want it to be right at 400 volts? We want the load to be at 400 volts and not 400.8, although 0.8 is not that far off. Remember the discussion at the beginning of the semester, who pays the bills? It's the consumer, the customer, this person right here. So if I've contracted with you to provide me energy and you don't provide it at the voltage, then I'm going to find a different supplier. I'm going to go someplace else and get the voltage that I need. So what happens is this voltage here has to be adjusted as necessary to provide whatever value I need. So the voltage is going to have to be 400.8 volts. What happens when the load trips offline? Let's just say the customer has some sort of a fault condition in their plant and they go ahead and they trip the plant. What happens to the load? Goes to zero, doesn't it? No more current because there's no connection, which means the voltage drop across here now goes to zero. And what is the voltage seen at the output? Not at the load, but at the output. It is the input voltage as well. So the V no load would be under no load conditions. I have to set my supply so that I'm delivering 400.8 volts on the secondary of the transformer. The V full load is what the customer expects. So when I connect it up, I'm going to have 400. So my calculation is 400.8 minus 400 divided by 400 times 100%. I get 0.2% voltage regulation, which is pretty good. Normally, if you have less than 3% voltage regulation, that's considered acceptable. So 0.2%, this is a pretty low, it would be considered a pretty low internal impedance. The other thing to note is that these are magnitude onlys, okay? You don't do percent voltage regulation on angle that has no interest and no bearing on what you're doing. You do have some angle change here. And the reason why you have an angle change is, remember, this is an inductor. So the load only has P, but this has P plus JQ, right? Because it has an angle associated with it. So it's not unity power factor anymore. So where does the P go into the system? Where does the Q go? Doesn't go to the load. Yeah. How about in the transformer impedance? Remember we talked about leakage reactance? So we actually are consuming reactive power or consuming bars in the transformer to go ahead and deliver that rated power. That transformer is dragging down my sine wave, my average power over a cycle. So it's dragging it down. So power has to go back to the grid or back to the supply for periods of time through the sine wave. Yes, sir.
V no load always could be higher than V full load.
Yes, absolutely. Because if you have something in this box and current is going this way, I'm always going to get a plus to minus drop here when current flows. So whatever voltage is here, V in should always be higher than V out. V full load is always going to be assuming current through whatever that box is. The no load means the current goes to zero. So under no load conditions, you have no drops in your system. So V in should always be higher, except if the load has a leading power factor. So if the load has a leading power factor, what does that mean? What does Eli say about a leading power factor? Current leads the voltage. My power triangle looks like this, doesn't it? Q is negative. So there's Q actually going back in this direction. And so your voltage at your receiving end or the output end is actually higher under leading power factors. So it can be negative, but now it's very much dependent on the load. Most loads operate at a lagging power factor. That's why I said it's it should always be higher. But if you have a capacitive load, like if you're at a substation, you have a cat bank, then it could have a leading power factor. But every industrial facility here operates at a lagging power factor. It just wouldn't make sense to go leading. Good question. All right, here's another example. So we have a 75 kVA, 2400 to 240 volt transformer. So this could be something outside of your dorm. Campus has a 4160 volt underground distribution system. And if you take 4160 divided by square root of 3, you're going to end up with 2400 volts. So a lot of those single phase pad mounted transformers that are outside buildings, or if you were to go to some of the dorms, you don't see the transformers outside there because those are inside the actual building. And it used to be allowed that you could put transformers in the building because you wanted your low voltage stuff as close as possible to the panel boards because you could run a lot smaller cable. You had a higher voltage rating, but you could run much smaller cable. So if anybody knows my office in Barrows, there's a door right across my office that says danger, do not enter. What's inside there are three, literally, they're just pole mounted transformers as the cans that you see outside. And they're in that room and you can walk right up and touch live 4160 if you were so inclined to do so. I don't recommend it. But they actually have those pole mounted transformers actually inside the basement of Barrows at my location, right across from my office. That's not permitted anymore. We talked a little bit about it, but fire, right? You have oil-filled transformers. If those leak oil, you can actually get a fire in there and cause the building, to burn down. But remember when old Barrows was built was in the 60s, so you didn't have the same concerns as you do today. That's why the new Barrows, their transformer is located between Neville and the new section of Barrows. There's a transformer right next to the generator. And all that does is it has an oil-filled transformer. It's a pad mount. And then they step the voltage down to 208 into New Barrows. And that transformer is located completely outside. That's a lot more expensive, but nobody will insure the building unless otherwise. You'll also notice outside my office, out of the building, there's a little concrete step. So you actually have to walk up and in to the room that's where the transformers are, because if any oil spills, you want it to be in some sort of a containment. So they basically have a containment burn built into the flooring. And if you look, it's, I don't know, 4 or 6 inches right below the door so that all the oil would be contained inside there. So anyway, that would be the transformers that they have inside the basement of Barrows, 2400 to 240. This time we're going to have a real part and an imaginary part. So we have an R equivalent and an X equivalent. We wanted to determine, and this is where the change is, voltage regulation when we operate at full load, so driving this transformer at 75 kVA, and now we have a 0.85 lagging power factor. So we got to find the load, 312.5 at an angle of minus 31.7. Now we're going to add that voltage drop to the secondary side because this voltage is at 240 volts. So we're going to deliver. You have a question?
Yeah. Why we didn't divide by 240?
Because I'm delivering full load operation. I'm assuming I'm delivering it at 240 volt. It would be unlikely to deliver power to go from 240 to 2400 at this level at 75 kVA. So what I was saying is those transformers on campus, they take voltage in at 2400 volts and step it down to 240. So they can use it in your buildings or whatever. Okay. So my secondary voltage is 240. That's what I have to deliver to the customer. Here's my impedance. Here's my current. And I get 252 0.49. Now I run full volt, check out my voltage regulation, and now I'm getting 5.2%. This is probably too much voltage regulation. So I'll give you 5 minutes to redo this problem. Okay, give you 5 minutes to do a 0.85 leading. It's 11:24. We'll check back in at 11:29. So 5 minutes. Redo this problem at a 0.85 leading. While you're doing that, I will do my own. If I can see MATLAB. Yep, I'm going to just shrink it down a little bit. I'm going to do a new script. Sorry, I'm just making everything big. Okay, so huh? The second file? This one?
Yeah.
One more minute. I'm doing it right with you so you can prove that it can be done. All right, what'd you get? Anybody? Take you a bit longer? I did it in that time. Oh, that's great. 2.7 plus or minus? Minus 2.7. So going back to what he asked, can you get voltage regulation that's negative? Yes, if it's a leading power factor. And what was the only difference that you needed to do in this problem to do a leading power factor? That becomes a positive number. So I did this simultaneously in MATLAB, just because this is how you would do it on paper and pencil, right? With your calculator, if you entered on all those parameters. So you would just do, what is Z? What is the power factor? And you have to do all those steps. And so I basically entered it in, and then this is how you use Euler's or Euler's identity to enter in the value of S. I'm just going to go ahead and not display that. Here are my voltages, my calculate current, and then I display I. I actually don't need to display I. That's just for us to be able to see that hopefully we get 312.5 at an angle of plus 32. And then I also display my full load because I want to see if we get what the voltage is here. And then the last thing is the equation is what I do over here. So that's literally just kind of the step-by-step process. So if I run it, hopefully no typos. Sounds like there might be a typo. Let's see. So that usually means that I left out a parentheses. So try that again. Forgot to put abs here. And abs here, because I only need the magnitude. And that's what I got. So my current, whoops. Why is the current way off? The current says 554 at an angle of 0. Let me look at S real quick. Oh, anybody know what I made a mistake here? I got to use Euler's identity, so I have to multiply that by J, right?
For you.
So I forgot that there. Now I get 312.5. My voltage still says it's 252. Only gone down a little bit. Oh, I know why. Because this is a negative number. That should be negative here, because this is S. Right? So this is minus J times that. Try that again. So I got 312.5. I'm not getting a negative number though. Why is it not a negative number? $240 minus this. Let's see. V no load minus V full load. So 240 minus here. That should be greater than voltage. I'm getting 233. Let me try running that again, just so that I'm not messing something up. So I get the correct current.
Maybe you put 240 minus. Oh, good, that's not, it should be minus VS plus. Second one.
V no load minus V full load,
We know what is VS.
but the voltage on the secondary with that value should be higher. Why is it lower? So that's 312.5. That is a leading power factor.
So it should be 233.47 minus 240. Divided by 240.
Do I have it backwards? V no load minus V full load. So V no load. Oh, yes, you're right, because V full load is 240. Thank you. Should be this one.
Minus,
We got it backwards. This should be minus VS, and then this should be minus VS, or just VS.
yes, yes.
Okay, so it's good that we didn't have it. That's a quiz, right? I made some mistakes. But yeah, so now what you see is the voltage drops when you go from full load to no load, the actual voltage is reduced. And that's because you have a leading power factor. So that reactive power that you get from the load actually helps boost your voltage.
So when you have minus 2.7%,
Yeah,
not that you always positive.
you can go negative though. If you drop your voltage, can it be a negative?
Never heard of
If the, you never heard of a negative percentage, only because you've ever said, hey, the tank is 50% full. What if the tank could go less than 50% full? So what I mean by that is, what if you consider the tank is 50%, that's at 0%. Then anything above, it's positive. Anything below, it's negative. So that's the same thing that we're doing here. Okay, so that's how you can do it in MATLAB. Again, it's the same thing with the calculator. You just have to make sure you put the right numbers in the right equation. Yes, sir.
Do you need to include the angle when you're doing your voltage regulation?
No, just the magnitudes only. Yep. And I included my angles when I did my calculations, because by using Euler's identity here, that e to the j theta, that makes that a complex number. That's the magnitude and an angle. What about voltage? Do I have a magnitude and an angle here? The answer is
No.
angle 0. So 240 at an angle of 0 is 240. You can enter that in without multiplying it by e to the 0, j0, because it's just going to be 0. So when we think about it, if we operate things at a leading power factor from a load perspective, we actually can get more voltages. And that's what happens at night when your systems are very lightly loaded. You actually have some capacitance on your system, especially for underground cables. And if you don't have a lot of load on your system, you actually can get over voltages. And so that's why in the evening, sometimes you actually have to back things down. That's why we have what are called load cap changers, so that they're constantly adjusting, because sometimes you have too much voltage and you have to bring it down. So you're always, the grid is always adjusting itself to make sure that that voltage to the customer is right around nominal. And they'll clink up or down as necessary, because going up or down by 10% in the utility world is not that big a deal. Going up or down by more than 10% becomes an issue. But again, the customers have to be within that, usually it's within plus or minus 3%. And I think that that's a requirement by most utility companies.
So now, what if it was above the 3%? One.
If it goes above the 3% under emergency conditions, you can go up as far as 5%. But then they have to bring it back down to within the plus or minus 3% within a reasonable amount of time. You should never go above plus or minus 5%.
Why? What will happen?
So if you go above plus or minus 5%, it's possible that you could start to damage equipment. Sensitive electronic equipment could get damaged. Like if you look at the grid, they have surge arresters. And if the voltages go above maybe 10% of nominal, maybe 15%, they'll actually respond, because you get a switching transients. But there are cases where if you drive something at more than 5%, you might have an overvoltage condition, or you might be pulling in too much current. Remember, if we just put a resistor on there, The voltage goes up, the current increases, and you could damage it because you're running it at higher than nominal voltage. So that's why you have a tolerance of typically around plus or minus 3%. And if you are, those of you who went to the community college and did any classes with the National Electric Code, there are requirements about not letting the voltage drop on any device exceed 3%. So you have to reconfigure your design if you have really long cable runs to make sure that you're limiting that drop to less than 3%. Usually it's never a problem to go up, or usually hardly ever goes up. It almost always goes down. So lower voltages tend to be the issue, not higher voltages.
Interesting, because back home, the father you are away from the control, that's what you add.
Which makes sense. Yeah, if you're in a developing, I hope that's not derogatory, use the term developing to describe your home country. Whereas if it's developing versus developed, that just means that you're still evolving and getting different things. One of the key indicators of a developing versus a developed country is a stable and reliable electric power supply. Because if you're trying to make widgets and you're in a country that you can't always guarantee the power is going to be a certain value, or if it's even going to be on, how can you sell widgets if you don't know that it's going to be reliable? So what do you end up doing? You move to a country that is reliable, or you put your own generator on, which is very expensive and takes a lot of maintenance, and then you just don't do it. And what would be more reliable, having a generator or having the grid? The grid has maybe thousands of generators. What's the likelihood that all 1,000 is going to fail at the same time? Maybe if you had some really massive natural disaster or a war or something like that, where you would lose a lot of generation, okay, that would be the case. But under most circumstances, we might lose power at our house, but that's only because our connection to the grid has been lost. But the generation is still available to pick up the slack. It's just that we're not connected to the grid for one reason or another. So maintaining that generator, very expensive. I have a cheapy, Home Depot special that costs, I don't know, $1,000, but the generators we're talking about are multi-millions of dollars. They're properly maintained. They have a stable fuel supply. They've been proven to be maintained. Otherwise, ISOs won't allow them to dispatch on. So they're very reliable, as opposed to, that generator that I have in my backyard, that I fill it up with hopefully stabilized fuel every couple of months or something like that. Not always the best design. Yes, sir.
Just clarify with the full load versus no load.
Yep.
It should be the full load one that's the rated voltage, right?
The full load one is what you're actually delivering. Yep. The no load one is whatever it floats up or down to based on adjusting that supply. Yep. So here is, if you wanted a little more detail, this is the MATLAB script, doing it with a slightly different approach, but it does exactly the same thing. All right, so now let's connect some transformers in delta or Y's deltas. So remember, we build a single phase transformer, or we purchase a single phase transformer, and we can connect those in any manner we want, either a delta or Y, doesn't matter to us. And we would go ahead and we would actually do our work and literally physically connect the transformers. So here is a grounded Y. So here's our power supply. Actually, it's not even grounded. This is the incoming power supply, and we show it as a Y connected one, but it could be delta. And how do I know this is a Y? Because if these are my dotted windings, you notice the non-dotted windings all connect to a common point. So I have three physically separate transformers, those single phase pad mounted, pole mounted transformers. You can buy three independent ones, and then you could wire them up and you could get delta Y, Y delta, whatever you want. So it makes sense, if you can, to buy single phase transformers, because it's pretty easy to wire them up. That's why in the utility, if you drive up and down Stillwater Avenue, when you see three cans on a pole, that usually means it's able to provide three-phase power. And the reason why they have the three cans on a pole, not one can on a pole, is typically it's much easier from a maintenance perspective. If I've got three transformers, one of them fails, it's a lot easier to change out one smaller transformer than one bigger transformer. So, and under really important, reliable conditions, or really big applications, it's always better to go with three single-phase transformers. I was down at Clemson University many years ago, and that's how their electric supply is. they have 3 single-phase transformers, but campus is considered so important as a load, they actually have a 4th just sitting there, ready to be turned on and connected in. If you remember when we looked at, transformer tests, let's see if I have it in this class or is it a different class? I can't remember. It might be in a different one. Well, I know it's over here. So let me go back here. And let's see. So this is a transformer, and this is a fairly big transformer. Well, this is a 3-phase one. Do I have the other one? I was hoping to have the other one. I might not have it on this computer. Where is the transformer stuff that I have? Let's see. Let's work pretty on that one. All right, let's try this one. I think it's this one. No, that's a 3-phase. Sorry. I'm having a hard time finding it, but the one that I showed you for the nuclear power plant, I just can't seem to find it right off the top of my noggin. I thought it would be in here. Here. Oh. That's the generator.
Is it the one where we're looking at last class?
Separate one, slightly separate one. This is the generator, but I don't think I have the transformer stuff in here. Yeah, so this is for a nuclear plant in Connecticut. And in Connecticut, they actually have 3 single-phase transformers connected in whatever configuration they need. And anybody want to guess as to why they have 3 there? Does it have high reliability? It's just really big. That transformer has to be able to put out almost 500 MVA at full load conditions. A 500 MVA transformer is a massive transformer. You're probably going to have to ship that over rail and then rent a special truck to get it onto your facility. So in that case, you actually would buy 3 single-phase transformers because a 15 MVA, 100 MVA transformer would be, almost as big as a quarter of this building that we're in. You just couldn't ship it. So you would buy single-phase ones, and then you would just patch them in together there. The biggest 3-phase transformer I've ever seen, I think, was 900 MVA. And that one, when I was at Maine Yankee, that one got shipped in on a barge. So they were right up to, I don't remember what the inlet is, right off the ocean. And then they just brought it in on a barge, and then they just brought it up a hill and then parked it in place. So that one didn't get shipped by the rail. So that's what the other thing to think about is these transformers are physically big and they're heavy. They've got iron inside them. So it's not unheard of for a transformer to weigh 100 tons, 200 tons, which exceeds the limit for most applications. So you can't get there from here essentially. But here's our 3-phase transformer. So we take the 3 incoming windings, the dotted ends, and we run those to our power supply. And then the non-dotted ends, we connect it together. And the reason why we need this is because we need to make sure that current can somehow flow out of here and then return back to here. Well, if I connect all these to the same location, I can see here and here. At that point, the return current can go back through and go in that direction. And it's why, because you have the same connection on the secondary side. A YY transformer is very typical for like the utility connections because they provide ground locations, but they're not very common in industrial applications. And that'll make more sense if you take the follow-on class for this one. But look at the loads. You can have delta or Y connected loads, doesn't matter, doesn't care. That's the single phase equivalent diagram. And because we have Y connected transformers, this is 240 volt across here, but the actual voltage that I have is 240 times the square root of 3. So if I want to actually get the turns ratio, right, it's going to be 240 divided by 120, but the actual incoming voltage is 415 volts, line voltage, and the actual output line voltage is 208 volts. So if I want to represent this as a three-phase transformer, three 100 kVA transformers are capable of doing 3 times their nominal amount, so 300 kVA. And this is the line voltage that I would specify across the transfer. So I can buy 3 100s, or I can buy a 300 with these turns ratios, and I get the same results. Yes, sir.
Yeah, we need to go back.
Sure.
So that we have 240 on the,
Primary side, across each individual winding is 240. Yep.
but then they said 240 times 3.
Is across 2 lines.
And then.
So each one of these would be 240, because this is from neutral, and you can see that I have a neutral point right here. So I'm applying phase to neutral across each transformer line.
And then on the output, you have 120.
Yep, because each transformer independently can step voltage from 240 to 120. But once you start connecting and looking across 2 of the phases, then you get the square root of 3, both on the primary and the secondary side.
So you, for VLS, you get 120 times 3.
Exactly. Yep, that's shown right there. So you get 208 volts. So this is the physical representation of a 3-phase system. This is literally how you'd wire in the field. That's a lot of work. Why wouldn't I just do it this way? The single phase equivalent. I've got my source, my transformer, and 2 loads. And I can analyze the system just by looking at the single phase equivalent. Much, much easier. You can also do it from this perspective, but this is never really done in industry, because what wire is this? It's trying to indicate the neutral, isn't it? But the neutral doesn't often run. So you don't necessarily have that neutral connection. So a single line diagram is almost always shown like this. Very rare that you'll show a circuit diagram like this. This is if you wanted to analyze a circuit to figure out what's happening, but in reality, you would not show this as a in a field drawing.
And then what does the flash angle mean?
This is per phase, 25 kVA per phase. So if you want to do single phase equivalent calculations, you need to make sure that these are single phase quantities. So here's how you do delta Y. And it's hard to see, but try to be very explicit here. This transformer, its output voltage and current are going to be in phase with this transformer, okay? And it's plus to minus here, plus to minus here. So what I'm trying to do here is show you physically how they are so that you can actually get the phase relationships, because the voltage across this here, whoops, plus to minus like this, is exactly the same in phase as the voltage across there. Other than stepping down the voltage, you know, with a transformer turns ratio. Because one of the things that really gets confusing when you set up 3-phase transformers is, hey, I can put A, B, and C here, but there's nothing saying I can't switch A to B. I can move B to A. And now I have to be very careful, because that A may not be in phase with the A that comes in on the inside. So one of the things that's hard is transformer phasing, and it can get really confusing because it's just a utility that picks, this is phase A, this is phase B, this is phase C. So they pick phase A coming in, and then when they go to a transformer on the way out, they pick phase A, B, and C. But they gotta be consistent, because if you have the ability of connecting on another circuit and somehow closing them in, like here on campus, we have 2 feeds, top of campus, bottom of campus. We can't interconnect those because those 2 are never in phase with each other. In an ideal world, not even an ideal world, in a better setup, those two would actually be in phase with each other, so that in case the top of campus, the incoming power was out, you could run more of campus on the bottom circuit. Usually it's the other way around. The top of campus tends to be more reliable than the bottom of campus, and you could run all of campus off of this top section. They want to have that backup one down below campus to give a little bit more reliability and redundancy. So a few years ago, they had a bad problem up at the top of campus, and buildings were out of power for 2-3 days. So what they did is they started switching some of the load that used to be on the bottom of campus. They switched them to the top part of campus. And I don't know if they switched back, but there's a lot more load at the top part of campus than the bottom part of campus. And that'll make more sense when we start looking at phase shifts. But in a Y delta, we see that the voltage across two phases is not the voltage across these two phases, right? We have the turns ratio, but we see that there's a square root of 3 difference, because this voltage and this voltage are the same other than the turns ratio. So if I want to compare line to line voltages, if I'm looking at it from a perspective of a 3-phase transformer, I have to include that square root of 3. Okay. So that's why you see that the line voltage on the primary side is square root of 3 times the phase voltage, where over here, they're the same. So this is how you would physically wire it up if you're trying to look at angles and keep track of things. This bottom one is if you don't care about the angles. You're just going ahead and showing the transformers, and you're simplifying it. Again, you can see that this is a Y connected one because all the bottoms are connected to the same point. Over here, look what they do. They go through each other. So there is no neutral in that delta. They have to connect all the way through. So any current that comes in A and wants to return to B, some current can go through here, through that winding, and some actually might travel down and then return up through that leg as well. That's in our delta connected circuit. Here's a couple of things about the turns ratio. So the turns ratio, when you always compare the phase to phase, this is always the case. But if you look at it from a 3-phase perspective, if you're actually trying to get what the turns ratio is, because my line voltage is now for 3-phase, I've got a line primary and a line secondary. You'll notice that I've got 3 square root of 3 times that individual transformer turns ratio. So when I buy a 2400 to 240 volt transformer, if I connect it in Y delta, the actual transformer, if it was 3-phase, you'd write it as 2400. That's the actual 3-phase turns ratio, but each individual, whoops, I have an extra 0 here, but each individual transformer has a turns ratio of 10. Okay? So that's how we can reference the two. And you can see how you can actually specify your turns ratios that way. The other thing, and this is the hardest thing about using delta Y transformers, is you get a phase shift. And you have to get at least a 30-degree phase shift from primary to secondary. So remember how I said the top of campus is not in phase with the bottom of campus? The top of campus comes in. There's a transformer. It comes in at 46 kV, and it steps it down to 4160. That's the top of campus. The bottom of campus, it comes in at 12.47 to 4160. So why is there a phase difference? Because to get to 12.47, there was another transformer that went from 46 kV to 12.47. And these were all, that was probably delta Y, for introducing a 30-degree phase shift. So when I mentioned the top of campus can't connect to the bottom of campus, the reason being is because there's a 30-degree phase shift, and there's no way to get rid of that. Unless you swap out one of these transformers and make it YY. If you swapped out a transformer and made it YY, you wouldn't actually have that 30-degree phase shift. There's other way to do it, but that it would be more complicated to shift things back. So that's another reason why they want to move campus all the way to 46 kV, because then you don't have to worry about phase shift. The downside is you only have one incoming connection. And so the reason why you have that 30-degree phase shift kind of hard to see. But remember, if I'm looking at this voltage over here, which has VA on the primary minus, we'll call it VC. That's that voltage over here. VA to C over here is just from here to here, which is just this over here, right? So I don't have that 30-degree phase shift introduced. I just have this, which is basically going to be this voltage. It's just going to be that, whatever that voltage is. So you can see I have a 30-degree difference between those two. And that's just by adding the vectors. Anytime you go from a phase voltage to a line voltage in a Y connected circuit, you've got to have a 30 degrees. That's just because of the math. So that's the hard part about dealing with that. Okay. So you can connect Y to Ys in parallel because they're in phase with each other. And Y to delta, you can't connect those two. So a Y to Y connected to a Y delta, you can't get that because this is going to have a 30-degree phase shift on the secondary side, where this one doesn't have to have any phase shift. But if I have two of the same and they're both introducing 30-degree phase shifts, then it's perfectly no problem. I don't have a phase shift. I just got to make sure that I have A to A, B to B, and C to C. Here's another one with delta Y. It's the same concept. It's just that now what I see is my secondary has the square root of 3. So remember this turns ratio here to here. That's the A value. But if I'm looking at it from a three-phase perspective, I'm comparing V line primary to V line secondary. And that's why I end up with that square root of 3. Again, it's always V phase on the primary and V phase on the secondary is the turns ratio. Delta delta doesn't have a turns ratio. It doesn't have a phase shift. It doesn't have to have a phase shift. You can introduce a phase shift, but it doesn't have to because they're all in phase with each other. So let's see. What if we open the delta? So an open delta is, let's take those out of commission. Do I get three-phase power out of a system if I run two-phase transformers? How about not exactly, but sort of? Because what does KVL say? Some of the voltage drops on a closed loop have to be equal to 0. If I get 1 at an angle of 0 voltage drop over here, I get a 1 at an angle of voltage drop over here. This leg is open. What would I measure between these 2 points? So 1 at an angle of 0, 1 at an angle of 120. What do I measure for voltage there? 1 at an angle of 240. So I do get a three-phase voltage. I'm just not truly getting a three-phase power. But the reason why you do this is you're trying to save money. So you used to see a lot more of these open delta circuits on what are called instrument transformer circuits, potential transformers, because all I need is the voltage. If I just want the phase voltage, you'd see open delta ones all day long. But those are becoming less and less common because once you use an open delta, you filter out some things that actually could be really helpful. And so most of the time you're going away from just an open delta configuration, but it's a way to save a third of the cost. From a power perspective, if you do the math, I'm only getting 57.7% of the power of a three-phase transformer. Is that a problem? But with two transformers, shouldn't I get 2/3? If I get 2 out of 3, wouldn't it be reasonable to assume that I get 2/3 of it? You don't even get 2/3 out of it. You get less than 58%. So you actually don't have as much power as you think you do. Doesn't work so well. And then this Q1 talks about some of the Q stuff. You can get some issues. Yeah. All right. That's it for the world of transformers, three-phase transformers, connections. There are open deltas. There's also something called a broken delta. A broken delta, I'll do that really quickly. So an open delta, whoops, thought I did whiteboard. This is an open delta. You have two legs of the transformer. A broken delta is this. So you break the delta. So you have all three, but you break the delta. And the reason being, which will make a lot more sense to you in later classes, you have a current in here called the zero sequence current, that if you break the delta, you can actually measure I0 here once you break the delta. So that used to be very common back in the day too, when you were trying to look at ground fault currents. But now everybody does it this way because you can calculate what I0 needs to be. The relays today, the devices are smart enough to tell you I0 is this. They'll actually do a calculation for you. Where back in the old days, you didn't have the calculation capability. So you had to do all these tricks to give you positive sequence current, negative sequence current, zero sequence current. And so you can look at some of these old devices and they had all kinds of inductors and filtering and all that stuff built in to give you the characteristics you're looking for. So there's a lot of work back in the day. Nowadays, you can do it in one relay, except the relays have gotten incredibly complicated to set as it is. So kind of has a catch-22. Okay, any questions? Because we're done with transformers. So you should be able to finish the homework now. And this first exam is going to include everything up to including today. So don't forget on Thursday, come with any questions. You do have that exam review material that you want. We'll just go over whatever questions you have. We'll go through that. Go from there. Yes, sir. I can't hear you. Yes, I think it starts at 1, but if you want to talk now, I have time now.
Yeah, I mean, I got one.
It's up to you. We can talk now, or we can walk and talk back. Let me end the class and then we can talk.